Welcome to lesson 22. Today we're going to get started talking about some basic information on logarithms. And then in the next lesson we'll work with properties of logarithms, and then we'll go on in and work with equations and so forth. So let's get a good start on our basic ideas of logarithms. Well, I have a picture here of Mr. John Napier. He's considered the father of logarithms. And you can see he lived back around the late 1500s, early 1600s, and he wanted to come up with a better way to do computation because they didn't have their little calculators, handheld calculators back there. And so he started working with the idea of logarithms. Now, the way that Mr. Napier worked with them was very different than the way that we kind of see them today. He had some help from a guy by the name of Henry Briggs that came along and said, hey, how about that base 10? We might like that. And for other folks like me who come from pre-calculator age, which, believe it or not, did exist, we actually used those base 10 logarithms to do calculations in math classes and in science classes. Today we don't use them as much as a calculation tool, but we definitely still need logarithms because logarithms are now viewed as inverse of exponential functions, and it is in that capacity that they are so important to us. So here's an extremely important definition that you're going to want to grab a hold of. Log base b is the way that we read that. Log base b of x will equal y if and only if, our nice definition words, b, the base, raised to the y power is equal to x. You'll see that we're kind of turning around, we're switching input and output. The input and output got switched from an exponential function. And please do note b has to be bigger than 0. And it would be extremely boring if it were 1. Okay, so those are our limitations. Now, because of this particular information, notice that the output is this y, and look at where that output is sitting over here. The output of a logarithmic function is an exponent. You're going to hear that from me many, many times in the hopes that you'll be comfy with that. So let's use that definition from the last screen. Log base 2 of 8 will equal, well, I'll get us started, it's going to be 3. Why? Because 2 to the third power is equal to 8. So you see, this is the answer after it has been raised to the power. This is the base. And this is the exponent. Okay. So when we get to this second one, it's saying 3 raised to what exponent would give you a 9? That's how you reason that out. Well, that exponent would be 2 because 3 squared is 9. Now, if you need, back it up and go back over the previous screen and this so that you realize how these are being switched around. So now we say 25 raised to what power will give you an answer of 5? Well, now that one becomes a little bit scarier. We've got 25 raised to something is equal to 5, and you say, well, how does it get smaller? You might realize that, hey, the square root of 25 is 5. That would mean 1/2 power. So in fact, log base 25 of 5 is 1/2 because 25 to the 1/2 power will give you 5. A lot of times in logarithms, as you try to figure out what they're equal to, you've got to kind of do some backwards thinking. And number 4 here, log base 10 of 100,000. So the question is, to what power would you raise 10 so that the answer is 100,000? And I think you can see that's going to be a 5. Okay. Well, continuing on, because you know mathematicians, we like to get fractions and decimals and negatives. Log base 2 of 1/8. So the question is, 2 to what power will equal 1/8? And you might say, well, I'm in trouble there. I do know 2 to the third is 8. Okay, so what's going to put the 8 down in the denominator? Well, you might recall that that's due to a negative exponent. That by definition, a to the negative m is 1/a to the positive m. Okay, so in fact, in this case, we need a -3 because 2 to the third is going to give us that 8, but the negative is going to sit it down in the denominator for us. Okay? Well, then on 6, you look at this 0.01 and might be thrown by it for a moment. And there's more than one way to look at this, but I would think of the fraction. If you read this with place value, that would be log base 10 of 1/100th. And with that in mind, 10 raised to what power will be 1/100? Well, you realize that to get that down into the denominator, we need the negative exponent. It will be -2. Okay. Then for number 7, and you know why I like the number 7. If not, go back and check an earlier lesson. Log base 7 of 1/7. Well, the square root's going to make us think of what power? A 1/2. And because he's down in the denominator, it makes it -1/2. Because 7 raised to the -1/2 will be 1/7. You have to be good with your exponents to deal with the logs. Now, number 8 looks totally frightening because you're like, who wants to deal with powers of pi? But look carefully. Pi raised to what power will give you an answer of 1? Well, it's the same power that we would use for any of these other bases. It's 0. Because pi to the 0 is 1. Remember that by definition, any finite number other than 0, if you raise it to the 0 power, you get 1. All right, now that you've kind of got a hang of that, let's look at the graph, because we love to see the graphs. They're a picture of all possible values. And I've said let's graph y equals log base 2 of x. Now, before we get into domain and range, let's just start making a table of values. So let's see here. What if I let x be 2? Then the question is, log base 2 of 2 is going to equal what? So 2 to what power gives you 2? Well, that's 1. Now, as it turns out, it kind of dawns on us pretty quickly. It might be better to pick values for y, okay? Because here's what I've got. Y equals log base 2 of x, and it's kind of hard to keep thinking those guys backwards. But if I come out of the logarithms, that means 2 raised to the y power is x. So it really might be easier for me to just pick numbers for y. Like y could be 0. What's 2 to the 0? 1. Y could be 3. 2 to the third is 8. It does seem weird writing these backwards in our table. You just have to pay attention to what the y, what the x numbers are. Well, can I let y be a negative number? Yeah. If y is -1, I would have -1/2. If y is negative 2, I get a negative 1/4. What if y is negative 10? 2 to the negative 10? Well, I can tell you 2 to the 10th is 1,024, so that's going to be 1 over, oh, those aren't negative numbers. What was I thinking? 1 over 1,024. You don't get negative numbers with the negative powers, you just get the reciprocal. And let's just go ahead and plot what we have. We have 2, 1, 1, 0, 8, 3, 1/2, negative 1, 1/4, negative 2, and a very tiny, tiny, tiny fraction in negative 10. Well, you know what that makes it looks like we have going on here? Doesn't it look like we've got maybe a vertical asymptote happening? Now, by the way, I can connect the dots because I can actually have any number there for y. And let's think about that. I can have y be positive, negative, fractions, decimals. Now, granted, I have trouble figuring out those numbers, but with the aids of calculators or whatever, I can come up with a value. 2 raised to the 2.931. I can do that. Okay. But let's think about x for a minute. Are you ever going to get a value of 0 out of that? 2 to what power would give me a 0? That's not possible, is it? Your x values will always be positive quantities, okay? So my domain is 0 up to infinity. And my range, the set of all y's, we just argued I can have anything there as that exponent. It's all reals. Now look at the graph, and it does make sense that I have all reals. But it is very interesting that in the case of the logarithm function, it comes up here and it has this real steep climb. And then it hits the x-axis and it kind of takes a pretty wicked curve. And after it comes up through the axis, it starts to grow really quite slowly, which, by the way, makes it a very useful function for some of our scales in science. And as it turns out, as I let y go more and more and more negative, I am going to get closer and closer to that y-axis. So in fact, I have a vertical asymptote of x equals 0. Okay? We do in fact have that vertical asymptote. And even though it looks like there might be a horizontal asymptote, there is not, because we have been able to argue that this y value can be anything. So in fact, its range is all real numbers. It's just going to grow quite slowly there. Now, I had somebody make fun of me for saying things like this, but yes, it can be fun to graph y equal 2 to the x and just see what happens, okay? And you might say, well, why did she pick y equals 2 to the x? Can you tell me the relationship between these two functions? Notice that the x and the y's are switched, which means these two are inverses of each other. So let's see what that looks like. Let's see, we've graphed these before. All of those exponential functions go through the point 0, 1, assuming we have no transformations on them. They all have the x-axis as a horizontal asymptote, and then they turn and take a pretty wicked curve upward. And if you look really carefully, and my graph isn't perfectly drawn, but that line, y equals x, running up through there, you can see that these are reflections over that line. So as you are trying to work with the graphs of your log functions, realize that they're very closely connected to the graphs of the exponential functions, as any inverse functions would be. Okay, well, let's continue on and look at a different log. Now you'll notice here that I didn't write a base, and you might say, well, she just forgot. Well, no, actually I did not just forget. If we write log and there's no base indicated, then we just all agree that that is base 10. Base 10, also called common logs, and that's what those of us that are dinosaurs used to use to do our really big, nasty calculations. The kinds of things that you grab your calculator for today, I grabbed my log tables, my common log tables. Okay, so we're going to graph this, and I'm going to make a table of values, but if I have y equals log of x, I can put in numbers for x, but it's really hard to do all that backwards thinking. So why don't I just think 10 raised to the y has to equal x. And it's a little bit easier for me to create my table of values from there. So if y is 0, x is 1. If y is 1, x is 10. If y is 2, man, oh man, we're already to 100. Well, if we try negative 1, if y is negative 1, 10 to the negative 1 is 1/10. And at negative 2, I have 1/100th. I'll just stop there because already my numbers are getting kind of difficult to handle. So I have the point 1, 0. I have 10, 1. 100, comma 2. Yeah, I'm not going to graph that. Good gracious, that's all the way out there to 100 before it's gotten up to y value of 2. Yeah, I told you they do grow very slowly. And then, let's see here, 1/10, comma negative 1, and 1/100th, negative 2. Boy, it's bellying up there next to that y-axis very quickly. So it's coming up there very close to that axis, hits the point 1, 0, and whoa, shoots out there to the right. Took a really wicked curve as it went around there. Okay, now by the way, the other one also went through, the other one being our previous log function graph, went through the point 1, 0. Does it make sense that this point would be on all of our basic log functions? On the graphs of all of those? Reason being, any base to the 0 power will give you a 1. So 1, 0 will be a point on every single one of them. And then another point that's pretty good to pull off is when that y value is 1, you're going to get your base out. So you'll always have essentially your base, comma 1, as another point on every log graph. And they're all going to have this vertical asymptote of x equals 0. Because I can't get a 0 out of that, but I can get daggum close to it. Yeah? Again, my domain is 0 to infinity. And again, my range is all reals. Although I think you realize it's going to be very, very slow. In fact, let's see if you're on top of things. How far out do I have to go before this graph gets up to a y value of 3? For it to have a y value of 3, x is going to be 1,000. You got to go way the heck out there just to get to 3. And this thing is still going to go to infinity. It's just going to go very, very, very slowly. Now, if we graph the exponential function on there, which is in fact his inverse, boom. And again, you see that nice mirror image going between the two of those guys. All right? So hopefully you understand now that it doesn't matter what my base is, assuming I have no transformations on there, I should have a vertical asymptote of the y-axis, and I should go through this point 1, 0, take a pretty wicked turn. Yeah? Well, you knew this was coming. We get the basic, now we're going to put some transformations on it. So you look at this equation and you say, all right, if the plus 3 wasn't on there, yeah, I know what that guy's going to do. I know that he's going to go through the point 1, 0. I know he's going to just go straight up there, has that vertical asymptote, and he's going to hang a wicked curve to the right. Yeah? So then what's that plus 3 going to do? Well, you know what? It's going to do the same thing it did with our lines and our parabolas and our rationals and our exponentials and everything else we have graphed. It is going to lift it up 3 because that's our D number, that's our vertical shift. Now, technically, remember this is base 10, so I have the point 10, 1 and 1, 0. I would simply take those 2 points and move them up 3. So 1, 2, 3. I go to the point 1, 3. I go to the point 10, 4. And then there's my graph. This is the graph of y equals log x plus 3. Did his vertical asymptote move on us? Well, it's a little bit of a loaded question. Essentially, yes, he moved up 3, but because he's a line, we don't see any change in that. So my vertical asymptote is still x equals 0. Okay? Same kind of transformations you've been doing all along. It's kind of nice. You just get a new graph and do the same thing that we've done in the past. Well, another transformation problem. You see that if you take away that negative, the 2 and the 3, we would have y equals log base 2 of x. Well, we know he goes through the point 1, 0. And remember I said, along with the point 1, 0, that they all go through. The other point they all go through is b, comma 1, where b is its base. Well, in this case, his base is 2, so it goes through the point 2, 1. So here is the basic graph for log base 2 of x. Now you'll notice that I really have 3 transformations going on here. What will this negative do? Now that negative is a -1 for A, and you might remember that A is a vertical shift or compression. If it's negative, it flips it over the x-axis. So this will flip over x-axis. Okay. Then we have the 2 and the 3, and those are the horizontal and the vertical shift. The 2 is in parentheses with x, so he's horizontal, and 3 is outside, he's vertical. And you might remember that I talked about pre-op numbers and post-op numbers. Oh, that was a long time ago. In the case of the pre-op numbers, that's before you operate the function and you go opposite. So a +2 for a horizontal shift means I'm really going to go left 2. Oops. Left 2. Now this 3 is the D number. He's post-op, and you go according to the sign. We go down 3. Okay, so I got 3 things to do. I would like to first just do the flip, you know. So I would, that point stays put. This point, 2, 1, goes to 2, negative 1. And here is my second graph. This is my first. This is my second. And then all I need to do is take these 2 points and move them according to these shifts. So this guy goes left 2, down 3. This point at 2, negative 1 goes left 2 and down 3. Hey, did the asymptote move this time? And I mean more than just up and down. That asymptote was right along this axis. Now, in the process of doing my slides, do you realize he got moved left 2? So here is now my vertical asymptote. My vertical asymptote is x equals negative 2. And then my curve is going to look like that. This is my final curve. Okay? I took the basic log, I flipped him over the x-axis, and then I shifted him left 2 and down 3. Okay? Practice over those. They're really pretty easy once you get the hang of what the graph looks like. Okay? And ordinarily, we hit an exam with lots of different graphing on it, your rationals, your polynomials, your exponentials, your logarithmic. So make sure that you're comfortable with each of the basics and with what your transformations do to each of those basic graphs. Okay? Well, you know, when we start talking about logarithms, sometimes this little thing creeps into our work, and it's like ln(x). What is ln(x)? Well, you need to talk to the linguists as to why we do that backwards, ln. I think it's probably because of a different language, but it's for natural logarithms. And you might say, what the heck is a natural logarithm? Well, it is a logarithm in which the base is that guy we talked about in the previous lesson with the exponential functions. He is considered the natural exponential function. He's approximately 2.7, okay? And when we use him as a base in our logarithms, which we actually do quite a bit. And in fact, if you proceed on into calculus, you're really going to like these ln's most of the time. They're usually easier to work with in a calculus course than the log logarithms are. Okay? So if you can get comfortable with the idea, you see ln, it simply means it's a logarithm, it's base e. Okay? Now, with all of this in mind, now that we've kind of got a running start at what our logarithms are, let's try to come up with these guys without a calculator. Now, you might say, well, my calculator wouldn't tell it to me anyhow. Some do, some don't. Okay? We've actually seen this one before. Log base 25 of 5. What's a logarithm? A logarithm is an exponent. So I'm asking 25 raised to what exponent gives you 5? And the answer is 1/2. Why? Because 25 to the 1/2 is the same as the square root of 25, and that would be 5. Okay? Well, then let's see here. Log base 5. To what power do I raise 5 to get this? We've been here before. 1/2. Well, here I don't even know what the a is, but log base a of the square root of a, I know he's got to be 1/2. Because it's not asking me anything about the a number, it's asking me to what exponent would you raise that to get the square root of a. Well, now this one's going to be a little bit different. Log base 3 of the square root of 27. Any of you have it just right off the top of your head? Are you that lucky? Well, if I've got the square root of 27 and I'm trying to figure out that's 3 to what power? Well, you know that the square root of 27 is 27 raised to the 1/2 power. We've worked with that several times here now. Well, then you might realize 27 is a power of 3, isn't it? That would be 3 to the 3rd raised to the 1/2. And when you raise a power to a power, what do? We multiply those exponents. So the question was, to what power do we raise 3 to get this answer? To what power do I raise 3 to get the square root of 27? Well, that would be 3/2, or 1.5. Okay? Number 5. You may or may not be comfortable with this notation, and I'm pretty sure in a previous lesson we talked about this a little bit. The idea of the fractional exponents. If I have a raised to the m over n power, this denominator becomes the indexed on my root, and the numerator stays as the power. Now, sometimes it's more convenient to write it like that, and sometimes it's more convenient to essentially do the root process first and then raise the result up to the power. Either of these two are identical to each other, and that's the meaning of that fractional exponent. So when you see the cube root of some number, you realize that it's going to be that number to the 1/3 power. Okay? So, to what power are we raising 7 to get the cube root of 7? Well, that would be 1/3. Number 6 looks like I forgot something, but remember, if the base is not written and you see log, that is base 10. So this is really so obvious that sometimes it's hard. To what power would I raise 10 to get 10 to the 4th? Well, you're really staring at it. The answer is 4, because that was the exponent that it was raised to. But sometimes it's just uncomfortable. Same idea, log base a of a to the 5th. To what power do we raise a to get this answer? Well, that exponent is 5. And then on our last one on this page, we have ln. That's that natural log. So it means that it is a log. It is base e. The base doesn't get written ordinarily. So to what power do you raise e to get e to the 3rd? 3. Okay? And I said simplify e to the following again without a calculator. There's only probably one of those you could easily run on a calculator on all of them. Now in this guy, we've got 5 raised to some ugly, ugly exponent. So let's take a little bit of a look at that. Five raised to the log base 5 of 2. Now what I'd like to do is pull that exponent off for a moment. I'd like to do a substitution. We're going to let him be, let's say, k. So what I want k to equal log base 5 of 2. Now I know you might say, I have no idea why she would do that. Just go with me. Would you agree that it is okay for me to rename that? And if I rename it, then what I'm really looking for is 5 to the k, right? All right, now let's focus on this guy. By the definition of logarithms, this is equivalent to what exponential equation? 5 raised to the exponent of k equals 2. Isn't that what we had from way back at the very beginning of this? Well, now what was I looking for? I'm looking for 5 to the k. Well, I found it. 5 to the k is 2. So this particular statement is equal to 2. Wow. Again, sometimes they're so easy, they're hard. Let me have you look at this another way. This statement, log base 5 of 2, is saying this. To what power would you raise 5 to get an answer of 2? Well, I don't know what that power is. But if I raise 5 to that power, I've got to get 2. Do you realize that it's kind of a question answering itself? Okay. 10 raised to the log of 23. Now you know this is base 10. So this is saying the exponent to which I would raise 10 to get an answer of 23. Don't know what that is, but if I raise 10 to that value, I'm going to get 23. You might start to see the little game going on here. A raised to the log base a of 8 is going to be 8. Why? Because this is saying the exponent to which you would raise a in order to get an answer of 8. So if you do that, your answer is 8. And lastly, since this has a base of e and my logarithm up here has a base of e, guess what? It's w to the 3rd. If it drives you crazy, you might want to go get a drink of water and then come back and sit down and look at it again, because it is really easy. Don't make it seem worse than it is. Okay? Well, this looks like fun. We're supposed to simplify this, and I see quite a mess. Well, what does your algebra training tell you is the place to go first? Haven't you been pretty well trained that you're going to start on the inside here? So the question is, what is log base 5 of 25? Log base 5 of 25. To what exponent would I raise 5 to get an answer of 25? That would be 2. And because that value is 2, I simply replaced it. And now I need to know what's log base 4 of 2. So 4 raised to what power would give me an answer of 2? Well, it's got to get smaller, doesn't it? The square root of 4 is 2, so that is the 1/2 power. And then log base 2 of 1/2. Well, that 2's down in the denominator. -1. Hard to believe the log base 2 of the log base 4 of the log base 5 of 25 is -1. How cool is that? Okay? Well, let's go ahead at this point and just kind of recap our basic ideas of logarithms. And you want to make sure that you get in and you practice those problems so that you get comfortable with how we're turning these things around, okay? Because sometimes you're going to find it's more comfortable to be working in logarithms. Sometimes it's more comfortable to be working in exponential, and you have to be able to go back and forth between the two of them. A log is an exponent. A log is an exponent. Keep telling yourself that. Because sometimes you start seeing all of this garbage, ln's and logs and all these different bases, and you think it's some weird, strange, difficult thing. Just keep reminding yourself, logs are exponents. Logs are exponents. And move between these two forms to whichever one's going to be more helpful to you at the moment. Okay? The other really useful information here is the idea that the log function is the inverse of your exponential function. And so your graphs are related. You know, the horizontal asymptote on the exponential became the vertical asymptote on the logarithmic function. Every exponential function goes through that point 0, 1, the basic ones do, and all the basic logs go through 1, 0. Okay, so use that information and then, of course, use your transformations just like you have every other time. Okay? Well, in our next lesson, we'll go ahead and learn some of our properties of logs so that then we can get to the good stuff of actually putting them to use. I'll see you later.